Hello everyone, and welcome to our very first lecture of Math 311 Linear Algebra. Before we get started, I would like, if you haven't already done so, I'd like you to download and print the notes for this specific lecture. If you go to the, that's available on the checklist and also on the lecture notes module and on Western Online. I'm going to ask that you download and print these notes before viewing each lecture, because it'll really save you a lot of time where you don't have to write all this stuff on your own. A lot of this stuff is already there. Okay, so if we're ready to go, this first section and maybe the next section is going to contain probably a lot of stuff you've seen before, especially if you've had multivariate calculus, where you learned about adding vectors and some of the other operations involved. Okay, so that's what this first section is going to be about: the geometry and algebra of vectors. Okay, well, what is a vector? That's a kind of a definite complicated thing to say. We're just going to leave it right now to be a directed line segment. Of course, a vector can mean different things in different situations. But right now we're just going to talk about a directed line segment. And even this, there's some ambiguity, because are we talking about a line in 2 dimensions or 3 dimensions or more dimensions? Well, hopefully that will be clear from the context. Okay. The important thing is a directed line segment. So that means there's an initial point and a terminal point. Okay. And so if in this case, in the 2-dimensional case, we can see we can define a vector as just the vector that starts at this point A and ends at B. That's what we call AB. And if we say that it starts at the point -3, 2 and ends at 4, -1, then we can find the line. It's almost as mechanical as finding the slope of a line, but it's going to be a little different, because a slope, remember, is just one number, whereas in this case, this vector is going to consist of 2 numbers. Basically, it's the change in x will be the first coordinate, and the change of y would be the second coordinate. So we can say, if we say if the terminal point is the initial point is the tail, is -3, 2, and the terminal point is the head at 4, -1, we can subtract the x coordinates, 4 minus -3, and that's 7, and -1 minus 2 is -3, right? So we can see that this vector, as a directed line segment, we can denote it by these two components, 7 and -3. Notice that if you take this point, take A, and you add 7, -3 to it, -3 plus 7 is 4, and 2 minus plus -3 is -1. So you can see that. And of course, the order matters. If we made B the tail, and we had the vector from B to A, everything is reversed, right? We get -7 and 3. Okay, so order is important. And we say a vector is in standard position if its tail is at the origin. Okay, and then we should say that R2, maybe you've seen this notation before, R2, basically you can think of it as the whole xy plane, the Cartesian plane. But instead of x and y, we're going to use x1 and x2, just because we want to generalize this to more dimensions, right? So we define R2 as just to be the set of all directed lines or vectors of the form x1, x2, and now such that, that's what this colon means, such that x1 and x2 are elements in R. Okay, if you've seen this, you may or may not be familiar with this notation, this funny looking E. This just means is an element of. Okay, so another way of saying this is that x1 and x2 are just real numbers. So that's R2. And we can see that R2 basically corresponds to ordered pairs, okay, which is basically, the ordered pairs x, y that you learned in calculus. And that corresponds to all vectors with tails at the origin. Basically, if you take any point in the plane, there's a unique vector that connects up to the origin, and that the components of this vector are going to be the same as this point. So hopefully that's pretty clear. We're going to use square brackets to denote vectors. Okay, traditionally we'll use round brackets or parentheses to denote points. And then we say that the 0 vector in R2 is just the vector 0, 0. That's basically the only vector where the terminal point and the initial point are the same. And if we look, we can talk about column vectors and row vectors. And we're not really going to be, right now we're not going to be too concerned whether we write a vector as a row or a column. They obviously correspond to the same point in the plane, right? We could denote this as 5, 2 if we wanted to. But we're going to see that, yes, they're the same, but in some cases they're different, especially when we get into multiplying matrices together. But right now we're not going to make a big deal about this. So they're same and they're different, and yet they're the same. Okay. Now the two main operations we want to talk about today and for the rest of the course to do with vector addition and scalar multiplication. Okay. For vector addition, we're adding two vectors of the same length. Okay, so in this case, we're just talking about two-dimensional vectors, u and v, and we define their sum just to be the vector obtained by adding the corresponding components. So u plus v would be u1 plus v1, comma u2 plus v2. Okay, and geometrically, what this would mean is if u and v were vectors like this, that were not parallel or embedded each other or multiples of each other, these will determine a unique parallelogram, and then the sum is just going to be the diagonal of that parallelogram. And the reason why this works is if this directed line segment is really the same as this one, so we could actually write this as v. And you can see if we apply u and then apply v, we get the same point as if we were just to apply u plus v. Similarly, this vector is u, just in a different place, so v plus u is going to be the same as u plus v. So the same thing. So you can have that geometric interpretation for vector addition. For scalar multiplication, we need a vector and a real number. A scalar in this class is always going to be a real number. Okay. So if c is a real number and u is a vector, we define cu as just the vector obtained by multiplying all the components by c. And that has the effect of basically stretching or compressing a vector if c is positive. If c is negative, it would also involve reversing it in the other direction. So the note we see here is that if c is -1, we can define negative u is just -1 times u, and that's just the vector negative u1, negative u2. So in this case, if u is this way, then negative u would just basically the opposite direction, same length. We don't really officially define subtraction of vectors, but because subtraction really is just a special case of addition. Okay, we define u minus v just to be u plus negative v, which of course can be computed basically by subtraction, u1 minus v1 and u2 minus v2. And then we say, and then we have this geometric interpretation as well. We can see that if we apply u, rather in this case apply v first and then apply u minus v, we get the same places as if we just started here and applied u. Okay, and the same thing here. We can see that u plus v minus u is the same as v. Okay, so we have that geometrical situation. Now I mentioned parallel vectors. We say two vectors are parallel if one vector is a scalar multiple of each other. Like obviously you can see that these two vectors are parallel and so are these, right? And we can see that all these vectors are like this vector and this vector are parallel because 5, 15 can be written as 5 times 1, 3. And this can be written as negative 1/2 times 1, 3. And this can be written as pi times 1, 3. Okay, so all these vectors are parallel to 1, 3. And similarly, 1, 3 is going to be parallel to each of these vectors, right? Which is the scalars might be different, but the vector, they're still all multiples of each other. So that's what parallel vectors are. You go to the first example here. Example 1 on page 3. And this is really just going to be a case of doing arithmetic, right? So uv, in this case, u is negative 1, 4, and v is 3, 5. Okay, so then this is going to be, you can just add this as negative 1 plus 3, 4 plus 5, and we get 2, 9. 2u is going to be 2 times negative 1, 4. So this is going to be negative 2, 8. Okay, if my arithmetic is correct, and which is it's usually is, but it's not perfect. Okay, but don't worry, no one's going to flunk the course because of arithmetic errors. Negative 3v, this would be negative 3 times the vector 3, 5. So this would be negative 9, negative 15. U minus v would be negative 1, 4, minus 3, 5, which would be negative 1 minus 3 is negative 4, and 4 minus 5 is negative 1. Okay. And then finally, 5u plus 4v I think this would be negative 5 plus 12 is 7, and then 20 plus 20 is 40, I think. Okay. So we get 740. Okay. So really this is just arithmetic. You're just doing with 2 coordinates instead of 1. Now, we can generalize this. There's no reason why we can't generalize this. If you've had calculus before, or multivariate calculus before, you know what R3 is. It's 3-dimensional space. And we can generalize this. If n is a positive integer, we can always define Rn to be the set of all n-tuples. Okay, like this, where each xi is a real number. Okay, so Rn is so what we call this is a vector of length n. Okay, because there are n components. Okay, and that's what in fact the so this is an ordered n-tuple. Again, it's just a generalization of an ordered pair or an ordered triple, and xi is the ith component of x, or if you want to say it, you could think of it as the coordinate if you want. We'll use the word components, and we can define scalar vector addition and scalar multiplication the exact same way, right? We just add the corresponding components, and we get the sum of u plus b. We multiply all the components by c. We get cu in this case. Okay, so that's. Let's just do, if you want, you can do, look at this next example. So here, in this case, we are dealing with vectors in 3 dimensions, or vectors of length 3. Obviously, we can't. It's not possible to add, let's say, a vector of length 2 and a vector of length 3. Okay, so dimensions are important, right? So that means it's important that they both have the same number of components. But in this case, if you want to just pause the video, you can try this on your own. U plus b. So this would be negative 6, 1, 3 plus 0, 2, 4 and I think this is negative 6, 3, 7. 2 times u would be negative 12 to 6. Okay. Negative v would be negative 0 to 4. So this would be 0, negative 2, negative 4. Okay. Negative 0, we just treat that as 0. U minus v would be negative 6, 1, 3, minus 0, 2, 4. And that would be negative 6, negative 1, negative 1, I think. And then 3 times u plus 7v. Okay, what would this be? This would be negative 18. I'll add another step. Negative 18 plus 0. 3 times 1 plus 7 times 2. And then 3 times 3 plus 7 times 4. So that would be negative 18, 17, and 37. Right. If we do everything right. Okay. So again, this is just arithmetic. A slightly more interesting problem would be something like this, where the algebra is now coming into linear algebra, and in this case, we're trying to find a vector x such that 3x plus u is equal to 4v. By the way, that's why I put the little vector hat here, just to indicate it's a vector. Okay, and because we can't really use boldface like your book does, so that's what we'll be using in these notes, and you should do that in your homework too. All right, so when we have this, so the way we do this is let's write this equation in terms of its components. So this would be 3x. Now what is x? X is going to have 3 coordinates. So let's give them a name. Let's just call them x1, x2, x3. You could also use x, y, and z, or whatever letters you want. Okay. And then we have u is still negative 6, 1, 3. And we want this to be equal to 4v, which is 4 times 0, 2, 4. Okay. All right. Now let's simplify these. Let's simplify this expression on the left-hand side. This will be 3x1 minus 6, 3x2 plus 1, 3x3 plus 3. Okay. And on the right-hand side, this is going to be 0, 8, 16. Okay. Now, again, the only way 2 vectors can be equal is if all their corresponding components are equal. So 3x1 minus 6 has to be equal to 0. 3x2 plus 1 has to equal 8. And 3x3 plus 3 has to equal 16. So we have three very simple algebra equations to solve. This would mean this first one gives us 3x1 is equal to 6, so x1 has to be 2. Second one is 3x2 is 8 minus 1, that's 7, so x2 is 7/3. And 3x3 equals 13, so x3 is 13/3. Okay? So our solution, our vector x, is going to be 2, 7/3, 13/3. And yes, I prefer you write it this way. Don't write this. Don't write this as 2 1/3. We don't want to really do that. That's for cookbooks. Okay, so just use this as improper fractions. And don't use decimal places either if you don't have to. Okay. All right, because they're just fractions. Okay. And one more term for today is linear combination, which you may or may not have heard before. And when we talk about linear combinations, we're talking about linear combinations of vectors. So if v1 through vk are vectors in Rn, okay, so these are all ordered entiples, then a linear combination of these vectors is just another vector which is in the form of like this: c1 v1 plus c2 v2 dot 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 plus ck vk, where all the ci's are real numbers. Okay, so just to understand that the v's are vectors, the c's are real numbers, and the result will be a vector. That's what we mean by linear combination. Most obvious example is that any vector of length 2 will be a linear combination of 1, 0 plus 0, 1, right? Because we can write 5, negative 4 as 5 times 1, 0 plus negative 4 times 0, 1, right? This is because obviously this is the vector 5, 0, and this is the vector 0, negative 4. So we can add those together and get this. And in general, you know, if I have a vector xy, that can always be written as x times 1, 0 plus y times 0, 1. All right, so that's these two vectors we're eventually going to have a special name for it. It's called the standard basis of R2, but we're not there quite yet. We can also write the same vector as a linear combination of a different set of vectors, like in this case 1, 1 and 1, negative 1. Now for this we have to do a little bit more work. What we're trying to do is we're going to try to write this as something times 1, 1 plus something times 1, negative 1. Okay, in other words, in this case we'll let our scalars be whatever, let them be the vectors, the letters x and y. We want to find x times 1, 1 plus y times 1, negative 1. That's what we're trying to find, right? So what would if we expand this out? This is going to be negative 5, 4, or rather 5, negative 4 equals x plus y, x minus y. Okay, so, and then all of a sudden, if these vectors are equal, that means that 5 has to be equal to x plus y, and negative 4 has to be equal to x minus y. And then all of a sudden, we have a system of linear equations, which you should be all familiar with. You might have done that. Hopefully, you've done this before in algebra classes. We're going to see there are lots of ways to solve a systems of equations. Some of the methods are more complicated than others, depending on how many variables they are. But I think we can see that we can solve this by adding these two equations together, and the y's will cancel, and so we get 5 plus negative 4 is 1 equals 2x plus 0y. So x is going to be 1/2. And then we can plug x into one of these equations. We can say 5 equals 1/2 plus y. So 5 minus 1/2 is y, and get a common denominator. This is 10 halves minus 1/2. That's 9 halves. Okay. And so sure enough, we get 1/2 times 1, 1 plus 9 halves times 1, negative 1 is equal to 5, negative 4. Okay. Should get 9 halves. Right? And it's also going to turn out that any vector in R2 can actually be written as a linear combination of 1, 1 and 1, negative 1. Okay? And we're going to see that those are also an example of a basis, not a standard basis. Okay? But we're not quite there yet. But you can check that, pick any other vector and write it as a linear combination of these two. Now, you can't do this with any two vectors. Okay, you can't, for example, we can't write 5, negative 4 as a linear combination of 1, 1 and 2, 2. And The reason why for that is if we did, we'd have 5, negative 4 equals some number x times 1, 1 plus some number y times 2, 2. And doing the same thing we before, we have 5 is equal to x plus 2y, and negative 4 equals x plus 2y. And I think you can clearly see that this is not consistent. This has no solution because obviously x plus 2y equals x plus 2y, but 5 is not equal to negative 4, right? So there's no solution here. And so the answer to this problem is it's not possible. And the main reason is that this is 1, 1 and 2, 2 are multiples of each other. They're parallel. And 5, negative 4 is not. The only way that we could write this as a linear combination of these two vectors if this 5, negative 4 was a multiple of 1, 1 or 2, 2, which it's not. Okay, so congratulations for making it through our first lecture. What I'd like you to do now, or sometime soon, is I'm going to have you take a mini quiz just about this video and this section. It only consists of 3, or usually between 2 and 4 multiple choice questions. Okay, and there's just the most basic things possible, just to prove that you watched the video and that you're actually getting the basic idea. Okay, so you can that's on Western Online. You'll see that you have it's not timed, but you only get one attempt at it. And I am going to be asking you to almost everything is due on Sunday night except for the mini quiz. And this mini quiz mini quiz will usually be due to two days after the video is released. Okay, so I think for this one, I think it'll be due on Wednesday night. Okay, so you want to take care of that. Again, it shouldn't take you too long. Okay, so thank you everyone, and I will see you soon.